So we finally come to the last day of the conference. I'd like to thank you again all for coming. And this night is going to be devoted to CAD in practice. So we're finally going to see how people in architectural practice are using computer-aided architectural design. So we're going to start with Milos Dimcic. He is from a firm called Programming Architecture. He's going to talk a bit about it. And like I said the other days, I'm not going to read his bio. You can see it at the conference website. Okay? Thank you so much, Milos, for coming.
Hello, hello, yes. Okay, here we go. Test if this works. Okay. So, there's a phrase you probably heard a lot of times, that our DNA is 98% the same as the DNA of the chimpanzee. This means that all the things that we achieved, from Hubble telescope to the special theory of relativity, belongs to this 2% difference between us and the chimpanzees. And I always wondered, what can it be in this 2% that makes such a big difference? And for me, the main reason is this questioning. We heard... Okay.
Thank you.
I'll stand under the light. So, for me, the reason for this is the questioning, the things that we heard before, is this curiosity, is this drive to explore and to ask questions and to try to solve them. Einstein said that the important thing is not to stop questioning. And I think that this curiosity from the very, very early days, it's what drives human species and what drove me when I was a kid. When I was 7 or 8 years old, I got this as a present. It was a Commodore 64, one of the first commercial computers, after Spectrum and some others. And after a couple of weeks of playing video games, I realized I could do coding. There was a thing that was called Simon's Basic. It was an extension of the BASIC programming language written by a 16-year-old, written by a teenager in US. And this BASIC had some very simple commands that you can use and graphically display geometry, like these ones. And then I tried to do that, and I used them. And after a day or two, I got bored, and I actually started doing for loops and if loops, and I started drawing the rectangle snakes all over the screen. And it was very fun. I had no idea that I was actually doing parametric design in a very, very simple way. From then on, I went on to do different stuff. I finished elementary school, I finished high school. I enrolled into Architectural University in Belgrade, in Serbia, where I come from. And through this journey, I almost never programmed. And I will start explaining what happened after that. And it might be a bit confusing, it might be fast, but you have to bear with me and hope there will be a point at the end. And the reason I have this image up there is this point of connecting the dots that we all have to do. And I will show you basically now some of the dots that I created on the canvas of my life, and maybe think about how to make sense out of them. After the architectural faculty, I started my PhD at the Stuttgart University. My mentor was Professor Knippers, and I didn't have any finances, so I started working at his office. I worked there for about 2 years until I got the scholarship. I worked on several projects. This is probably the most important project. Is the Shenzhen Airport in China, designed by Massimiliano Fuxas, and office Knippers helping did the static analysis. And we started the first parametric software that appeared. It was called ParaCloud, and we started developing some parametric facade with the ParaCloud in the competition. in the competition time, and I said, we don't need PowerCloud, I can do this in RhinoScript, which I learned for only a month then. But I did it, we won the competition, and then we went on to design the whole thing and parametrically generate it. This is how it looks today. It was opened almost 2 years ago. And this is how the structure looks like. It has 400,000 structural members that are mostly different. And it has very complex facade elements that are not planar, that are not 2D, they're 3D. They're curved in space, and they're hexagonal, and they're approximately 4 meters by 3 meters, and you can imagine a 3D element populated over a double curved surface, and we always have to keep the glass surface flat. So that was a challenge. To make things more complicated, there were several types of elements with more glass surface, less glass surface, and Fuchsas usually used to paint how these elements should be distributed. We used these paintings and transferred them into Excel tables. That was also an input into the software. And this is how this is one picture from the construction phase that I wanted to show, to see where you can see the structure between and 2 layers of facade up and down. The point I want to make with this project is that a single person did all the programming. And that should show you the power of automation and the power of programming. A single person did the code that was used to automatically generate the entire structure and the entire facade of what is probably the largest parametrically generated structure in the world. And this is the small video that will just show you the process, so just so that you have an idea of how it was. We got these 2 surfaces from Fuchsas basically every 2 weeks, a new one, so that we have to regenerate the complete thing. 72 times, I think, we regenerated the complete thing, and that's the power of automation. We just got these 2 surfaces, which I then used to create a parametric grid. And this parametric grid was later on used to populate the structure and populate the facade. The element, as I said, was aluminum glass. It was a 3-dimensional element on the top and on the bottom layer of the structure. We had several types of elements based on the coverage, because the sunlight is a big factor in Shenzhen, and based on the angle, again because of the sunlight. These different types were transferred into numbers, then different influences were considered so that these numbers are populated over Excel tables, and these Excel tables were used as an input to the software that will populate the entire facade. We could easily control it, test it for the sunlight and for different stuff. And now you will just shortly see how it worked then. I have to remind you, this is, you can see in the corner, this is 2008, and this was mostly RhinoScript then, which means that it was pretty slow. Now this is not much faster. This is just how it looked then when the structure was made, and then it was cool to show these kind of things. Now we cannot show because it's basically made instantaneously. These are the algorithms that go several times and try to find errors, because imagine you have different types of elements and they have to be connected seamlessly. So the algorithms search for errors, correct them, search for glass panels that are not flat and correct them. So 7-8 different algorithms go through until you finally have the population of facade panels, 3D facade panels over double curved surface with all the glass elements flat. Anyway, during that time we were talking about my thesis and what I should do. And while I was at the Dnipro-Selbik office, I worked on several free-form roofs. This is one of the roofs that I worked on. It's the Maizal Mall in Frankfurt, designed by Fuchsas. You don't see really the roof here. I hope most of you know it. It's a very, very famous free-form grid shell. And Professor Knipper said, look, we have this column here, and all the stresses come into this column. But we make a grid shell pretty regular. We have triangles that are the same everywhere. That doesn't make statical sense. In the future, we should do something about it. Then, when I thought about what he said, and then when I looked at the natural structures, I realized that, of course, he's right. The nature designs in a different way. The nature enlarges density, where the static analysis needs it, basically. And it's not constrained by some prefabrication rules that we have. And the prefabrication rules are something that we are not constrained either, because all of these structural members are different anyway. So why keep them so uniform when it is statically not acceptable? While I was developing this idea, we were working on this Expo Axis project in Shenzhen, for which I, working at the office, I designed this grid structure. And we used some fairly simple methods for that time. We divided the whole structure into the big triangles, the small triangles, and then we used something that's called forced density method to relax the structure while keeping it on the surface. I don't have the time to explain what that is, but I will show you how I use that later. With this relaxation process, we could also change the tension in members. So this roof, this membrane roof, which is the largest membrane roof in the world, is connected to these funnels in 3 points. So by changing the tension of members, we were able to pull the mesh toward those points, so we get greater statical stability. And that was already in the direction of what I wanted to do in my PhD, as in form of a structural optimization. But then I thought, we are very limited with these triangular and quadrangular meshes. That doesn't really work. If you start pushing them around, they're very ugly, and it doesn't produce the results you want. What does nature do? Everybody knows now about Voronoi diagrams, and they're the basic natural pattern. And the cool thing about Voronoi diagrams is that if you have a regular disposition of points, you have a regular grid. So these 3 are also Voronoi diagrams, also created with the Voronoi diagram algorithm, only with a regular disposition of points. Voronoi diagram is very natural if you, from the micro to the macro level, if you imagine cells multiplying and fighting for space, basically the Voronoi diagram is what happens on their borders. Again, I don't have time to go into it, but I chose to use Voronoi diagram because by populating points over a surface, I could generate any type of grid. And we know that the NURBS surfaces are parametric. They are defined over U and V parameters. Only 2 parameters, so we can do simple transformation for x, y, from plane to the NURBS, and we can map anything that's in 2D onto the surface. But then I thought, this Voronoi diagram is really statically not acceptable. If you look at these cells, they're very irregular. You have some very small members and you have some very big members, and then the angle difference is big. And then I thought, why don't I use this relaxation tool to relax Voronoi over the surface, keeping it on the surface, which I did. And this type of structure I called Voronex in my PhD. And this type of structure basically imitates what foam does. Voronoi exists in nature in this very slow process of growth, and it doesn't have time to readjust itself. But the foam does it in real time. And basically that's the same thing that Voronex does. So I created the Voronoi structure some years later. This is how it looks when you relax Voronoi diagram, basically. And it shows how cells are now pretty regular, and they have within one cell, regular members, regular angles, and you can do it over any free-form surface. I used it to create a free plugin for Rhino. Most of you know that you can actually download the plugin and use it yourself to create any Voronex surface. The most important thing, as my professor Knipper said, what did I do with this Voronex pattern, is to shift the mind from designing grid structures with members and joints. Instead, now we can think of designing grid structures with cells, like nature does. And we can combine regular and natural patterns. So basically, you don't have to think about those directions of lines or the standard line joint thinking. Now you think like nature does. You think in density terms. You increase density when you need it, you decrease it when you don't need it. I'm going to make a short digression from the subject, just to show you that this year we're working on some pavilion that will soon be erected, that uses the Voronex structure, together with Paul Architects and the university in Saarbrücken. And I just extended a bit this plugin for Voronex to control the cells, so we can create some depth. These depths are then in proportion with the size of the cells and stuff like that, because we took some inspiration from the nature and the cells of the wood, because that was the task. And after some application of mesh smoothing, we are going to do to do something like this. These are the first prototypes from the factory, but I think in the next couple of months the pavilions will be erected. There will be many of them in the forest in Saarbrücken. To come back to the point, as I said, this was just a short digression. I created this Voronex pattern, natural pattern, but I was still far away from the structural optimization. I had to optimize it somehow, which means you need an optimization process. There are many of them, and I chose the stochastic solution. I chose to use evolutionary algorithms, genetic algorithms. They are based on the process of natural selection defined by Darwin. I can't get into it, there's a whole lecture on its own, but it basically creates generations of solutions randomly and then crosses them over, evaluates them, and then in generations and in generations you get the survival of the fittest solution, so to speak, based on your criteria. Many people are here familiar with it because genetic algorithms and evolutionary algorithms are very popular now, and they, together with the neural networks, are the fundamental of artificial intelligence. They're the basis of every artificial intelligence algorithm. So, in my PhD I created the software. This was my desire, how it should look, and this is exactly how it looked at the end, so that you can select your surface or design your surface. So we did not do form finding, because there are many research of form finding, and with our experience with architects, we said we're going to keep the surface fixed and try to optimize grid over the fixed surface. So you choose the surface, you choose the pattern that you like, you choose some static analysis conditions like support, load, whatever you want, material, cross-section of members. You choose the fitness. Of course, fitness was usually static analysis. Fitness, it was minimize the stress or maximize stability or minimize deformation. You choose penalties. Penalties work very well in genetic algorithms. You can say what the minimal or maximal size of the member or cell should be, and those solutions are penalized and they don't survive. So you set all the genetic algorithms settings, and you let the computer tell you what's the optimized structure for that form. The most important thing is that I made a very, very fast connection between CAD programs, in this case Rhino, and a static analysis program. It was all programmed in C++, and it was extremely fast. A structure of 1,000 structural members could be completely generated, prepared for static analysis, calculated within 1/10 of a second. So within 1 hour we could actually analyze tens of thousands of structures. This is approximately how it looks. Exactly this is what I said, only visually. You design a freeform surface, you select one pattern, you define static analysis. This is like, for example, export on all 4 edges. We have gravity and wind, for example. And you select your material, you select the cross-section of the structural members, you select your fitness criteria, minimize stress, for example, and some penalty, some limits that you want to impose on your structure. Then you let the genetic algorithms do their own thing. They generate thousands and thousands, maybe on an average calculation for a couple of hours you have like 100,000 solutions. And then when your graph starts to converge, which means you got to some very good solution, and you take that solution and you can analyze it, and you can think about how to design your structure. The results were amazing, actually. This just shows that you can analyze the cell disposition, like in nature, realize how to make the structure. And the results were amazing. As I said, you have the same freeform, you have the same number of structural members, joints, everything the same. The only difference is the disposition of structural members. And when you compare, for example, this structure with a regular hexagonal structure, you get 5 times less deformation or 2 times less stress in the structure. It was really, the results were surprising. And what we wanted to do is to show that our intuition actually doesn't work. I basically made some examples, very simple examples, where the intuition does work, to show that the software does produce logical results. Made a simple flat wall with the wind load, and when I fixed it on 4 corners and took the generation number 350 and put all the solutions of one generation one behind another, it showed me the clear tendency of the evolution. And it was what we would expect. It stiffens it stiffens the grid there where there are no supports. In this formation, it makes the X, which it showed us that the software works, but for freeform surfaces, we had no idea what to do. Our intuition didn't help anymore, and that's why we had to ask the computer what to do. And that's basically what I started with, is these questions, except we're in the age now where we can ask the questions that we can't answer, but maybe someone else can answer for us. So I got really entangled with this idea, and I started thinking about the weak artificial intelligence software that I could make. Just for the ones who don't know, there's a difference between strong artificial intelligence and weak artificial intelligence. Strong one is the one that people usually think of when they refer to it. It's the one that surpasses human capabilities. Weak artificial intelligence is the one that's only concentrated on one single area of exploration. So I thought about the software, and I'm still thinking about it, in which we can create structures with their own DNA, and we can let them evolve, and we can put different criteria, and we can let them grow on their own, except that it would be a feedback loop between machine and the computer. You will let the machine suggest something, then you would say no, you would correct it, impose different conditions, then the machine would do a million calculations behind it and suggest something again, and in this feedback loop, you would get to the solution. So it's a computer as an advisor, basically. So to answer questions that we cannot answer ourselves, the weak artificial intelligence. After all that dreaming at the end of the PhD, I had to pay my bills because the PhD was over, the scholarship was over, so I had to get back to Earth. I created my own company. I decided I don't want to work for anyone for several reasons, but one logical reason was that what I did, no office at the time needed that constantly. So I said, why should I work for one office and wait when something comes, when I don't have work, I have to do something else? No, I'll be on my own, and then I offer these services to several other offices. And in the last 4 years, I worked on some very, very interesting projects. I got my hands dirty, sort of speaking, in the real world. For the Baku crystal hole, this is what you see here in Azerbaijan. I worked for a company called Zele, and I wrote a simple code that generated thousands of elements like this. Many of them were unique, so they went into the production immediately. Otherwise, they would actually have to be drawn by hand, and thousands of these by hand, you need like 10 minutes per one. I saved literally thousands of hours, as they told me. Soon afterwards, I wanted to incorporate the static analysis knowledge that I know. So with Engelsmann, Peters, from Stuttgart, the structural engineers for Zelle, we did this Apple stairs study. As you know, Apple stores have these spiral glass stairs in most of their buildings, but their dimensions differ always. So when they change the geometry a bit, then the engineers need 8 weeks to make a structural model from it. So what I did was I parameterized the stairs, but not only geometry, but static as well, which means that this, what you see generated live here, is a 30,000 structural member statical model, which means once you define everything you need, you press one button and the model is prepared for static analysis. You don't need those 8 weeks anymore to build the model in the statical software from zero. And once it zooms in, yeah, you can maybe even see that there are many, many structural details. The statical model is very, very different from the geometrical model. I worked on a project by Zaha Hadid, Kapsark. This is a very complex project and the most difficult algorithm that I wrote, but I don't have time to present it. I just can tell you what it was about. These facade elements, there were concrete facade elements that covered the entire research center, and they had some thousands of them in some form of CATIA models, but they didn't know if they fit back in 3D. It was a mistake of the whole organization, so I made a software that imports automatically CATIA model, recognizes the shape by using some smart algorithms, finds its space in 3D, and pushes back there, and finds if it fits. We found tons of errors and saved a lot of money, but this is exactly the example of the mistakes that happen when you don't incorporate programmer from the very beginning in the projects like this that are complex. If you incorporate programmer from the beginning, and he follows you during the design process. Once the design process stops and everything else begins, it explodes. It can be extremely fast, but the problem is that we're always called at the end, and then it takes time. I will jump to another project that is the Schuko parametric facade system. The Schuko is the facade company from Germany, worldwide famous, and they are developing this parametric facade system where the architects can basically design their building using the one type of the facade, and they can vary some points. In this case, they can vary these 2 points in space and generate their geometry. Of course, this is only one type of the element. There are many types, including the triangular type. So far we're working with 15 different types. And the problem is that they didn't know what happens to the static analysis. So I had to automate the process first to find the worst case and the best case so they can calculate it. But then they asked me what happens if we have a fixed aluminum profile? What geometries can we generate with that profile? So I made an algorithm that makes models like that. You can't see here, but it's a pretty complex model. It has like 2,000 structural members. And it tests lots of geometries and basically creates a point cloud of the solution that are not statically acceptable for that specific aluminum profile. So the architect, if he chooses that profile and that frame, he has exactly graphically shown the area, the red area and the green area, where he can design his facade element and where he can not. I also use static analysis in a very innovative way in the Chadstone Mall in Melbourne. It's a project being done right now. And just so you know, engineers usually, when they do static analysis for glass, this is what the main subject was here. It was the 3,000 glass surfaces that cover this grid shell roof. They estimate which is the worst case. Which glass is the worst, and they do the static analysis for that, or maybe for 2 or 3 more, and that's it, they extrapolate. In this case, it was really hard to do, so I said, why don't we calculate all the glass elements at once? So I programmed it, and through a loop, we calculated all 3,000 glass elements, and there was no room for error anymore. So again, I started to dream, again I started to drift off. I started thinking about how to generalize this software. Maybe I can make it to work on any scale. For furniture, how about if I make a software where you can make a geometry and make any part of the geometry variable, whatever you want. Just let it vary, and in a loop, it will statically analyze that element, and using genetic algorithms or something like that, it will offer you the best possible solution. Sorry. Yes, again, I was pinned back down to the earth, and the project that manifests this pretty clearly is the New Foster building. It's the Bloomberg Place in London, and I work for Zela, the company that actually builds this project, and I again automatically generate many different elements, steel elements. I will give you an example. This is just some balustrade. There are many of these balustrades in 6-7 levels, and for some reason that I don't want to go into, they're all different, and you have some complex steel structures that hold those balustrades, and again they're all different from various reasons. They have different heights. We're talking about hundreds and hundreds of different steel elements. So I made a software that used all these incredibly complex conditions to generate this 3D geometry, and at the end to generate a 2D geometry. And at the end, what we give them is actually this. We give them PDFs with hundreds and hundreds of files like this. And although 95% of this is generated automatically, this 5% that has to be done by hand, someone has to see if the dimensions overlap, or if the stamp is good, something like that, it's killing us. It takes weeks, because there are so many elements. And then I asked them, listen, the things that you actually need to produce these elements, we had them at the very beginning. I generated them instantly. Now we're losing weeks and months to produce these PDFs that you don't need. for CNC machines. And they told me that they needed some sort of a control, and they still don't know who they're going to hire to cut them, so maybe they ask for PDFs and some stupid reasons that actually undermine everything my philosophy stands for. It undermines the fundamentals of my ideas that I had when I based my company. And that made me think, actually, what I am doing or what we are doing. And in my thoughts, this is basically how it looks, how I see it. 100 years ago, we could have built a building like this, and it cost something. And if we wanted to build a building like this, it costs 100 times more, and that's why we didn't do it. Even if we tried to do something like Sagrada Familia, we saw what an effort that is and how much work it takes. And I feel that what we did now is lower the costs of this. It's still much more expensive, but we lowered it. But is this good enough? If you ask me, by far not good enough. So, because no one says that this is better. There is no argument still that says that this is better and why we should give more money for it. So, I was thinking, what can we do? What is our goal? Should we try to do this for the same cost as this? Okay, let's try to do it. But you see what's on the way, those PDFs and stuff like that. You see that how slow the industry is changing. And that stands on the way and will stand on the way for a long time, I dread. But even if we did it, is this good enough? If you ask me, again not, because again, no one says that this is intrinsically better. And I think we should concentrate more on two things. One thing is the sustainability and the energy efficiency of our building. And I think that we should use this enormous, powerful tool that you have, that is automation, to increase this energy efficiency of our building. Other thing that I think we need to do is to deal somehow with this cultural identity, because we saw on some lectures before how buildings look the same everywhere, and how some expensive buildings look like spaceships just put there in the middle of the cities. Maybe we could use this automation tool, maybe for ornament, or maybe for things like that, to bring back the cultural identity and to make the architecture a bit more diverse and closer to where it comes from. For this second part, I don't have any ideas, and I didn't do much except for some ornament plugins that I'm not going to go into now. But for this, I did a bit. For an electrical engineer company, I was actually hired to do shadow calculations for these solar trackers that follow the sun. And when you have these solar trackers, you cannot avoid shadow. They always throw shadow on each other. If you space them too much, then it's not efficient. So I had to calculate geometrically how it works, and I gave them kilometer-long Excel tables that for every little module like this, for every minute of the day, they got the calculation how much are they in the shadow and how much in the sun, in percentages. So I used this knowledge to make another plugin that is for Rhino, that is also free, that you can download, that actually calculates shadows, but not as rendering calculates shadows with pixels. It actually extracts the form of a shadow in form of geometry. So you can use it in a loop, in an automated process, and calculate the square footage, the percentages, whatever you need to optimize your project. It's downloaded a lot. So I still don't know how much it is used and in what ways it is used, but I'm told it is used a lot. I thought, okay, when I did the sun, let's go a bit further. I had this idea for a rain simulation tool, and the algorithms for rain simulation are pretty easy. So in a day or two, I just made a plugin that is also free, and you can download, that you can use to do some type of rain simulation, look at the rain pads, and then examine your model and see if you actually have any problems, if the water stays somewhere, or it creates streams. And it was just an interesting interesting plugin to make because it was easy and it looks nice. So, the point I'm trying to make, from the beginning I said it's going to be confusing, I said it's going to be fast, and that I will try to make sense of it. But I can't make sense of it myself, because I feel stretched. I feel stretched between this idea that we have to deal with some big problems in the world, like global warming, sustainability. They're really, and we have this enormous power of automation, and I feel we're not using it right. And with this idea, I created these small plugins and I'm exploring, but I still don't know how we can actually use this. And I beg you to think about it. On the other hand, I know exactly how to make this artificial intelligence software, but it takes a lot of time. It takes a lot of time, it takes a lot of resources that I don't have right now. And stretched between these two things, I find myself in the last 4 years in the middle, going on this road that you basically saw, doing different things and waiting for the dots to connect and to make sense out of it all. And we talked about architectural profession. I think we can't talk about architectural profession anymore. I think that what we do is so interdisciplinary. It's so full of dots all around that we all create our own professional identity. I don't think we can stick a label to it anymore. I don't think I can say I'm an architect. I don't think I can say I'm a programmer. I can't put a label anymore. And I think we can't put a label on the profession anymore. Just go with it and admit and realize that we create our own professional identity and we all differ from each other. If you took one thing from what I did, I'm already something else. And in this sense, I invite you to step back a bit. I feel that with this programming, we're generating all these pretty pictures and doing all this grasshopper spaghetti and everything, but somehow I feel that we are lost among the trees. And I feel that we don't see the forest for the trees. So I think we have to step back a bit and look at the big picture and think about the big problems and finally find a way to employ this enormous power that we have of automation that I hope I demonstrated by showing what one person can do. This enormous power to solve some big and burning problems in the world. Thank you very much. I usually finish a bit earlier, always, I'm very fast, but I like it like that because I like to answer questions when there are some.
We have time for questions, so it's good we are not in a rush. So, any questions? Because I think this lecture can raise a lot of discussion. We are starting this type of discussion in Brazil. It's something very recent here, so I would like to know if somebody has questions. Thank you very much, Milos. It was a very nice lecture. Thank you.
Hi, Milos, right?
Yeah.
Milos? Okay. My name is Rodrigo, and it's just a simple question. I have been very interested about your work. I've downloaded your thesis, and in your blog you say that architects don't need to learn how to code. Mm-hmm. And it seems that behind this job there's a lot of coding. Yeah. So my question is, if someone wants to know what he's doing besides the rhinoceros spaghetti, the grasshopper spaghetti as you have mentioned, isn't it important to learn how to code?
Yes, it is. The point of the blog you're referring to is very delicate, and I was afraid that it might be understood in that way. I think that everybody should learn how to code. I think coding is the new English, basically. Like everybody needs to know English now. Everybody has to learn how to code. What I was referring to in that blog is that this, what I'm doing, is becoming so complicated that you should not have illusions in a way that an architect will be able to program on that level. In order for me to program on that level, I have to sacrifice an architect in me.
Okay, I see.
I'm not an architect anymore. I don't do architecture, I don't do architectural practice because I code 10 hours a day. So in that sense, I thought that an architect, if you're an architect, if you have architecture as your profession, you should learn how to code, but this is becoming very complex and it needs the creation of a new profession of experts in this field, because you have 24 hours a day. You cannot cover everything.
Okay, now see, that's why you have mentioned that nowadays we're going to have lots of professions and not equal architects.
Yes,
okay.
I mean, yeah.
Thank you. That's it.
Other questions? Yes, over there.
Thank you very much, Milos, for your presentation. Liked it a lot. So you basically say it's related to the previous question. It's actually going to be a hard question, something you might not want to respond to. So you're basically saying that every architect should do some coding, or at least hire a programmer from the start. I very much like that. And I think 90% of this room is actually in education. So what would you recommend us to do? Because if we talk to students and we talk about programming, like first year, second year students, I think 70% of the students just rushes out of the room. Do we make specialized schools, or what would you recommend?
Yes, the short answer would be yes. The bit longer answer is that this kind of complexity you cannot incorporate into architectural studies. You have to at least make a complete master out of it, or eventually the complete curriculum. So I don't think it can be incorporated. What must and should be incorporated is this simple way of coding so that people understand it, grasshopper and things like that, so that people get used to the computational thinking. Like mathematics is different in elementary school, so that you get used to the logic and mathematical thinking, because it's very important. So computational thinking is in the way new English, as I said, it's something that everybody has to have, and everybody will have to do some type of coding in the future, in their line of work, usually. So yeah, I don't think it can be incorporated in the curriculum on this level, and this level already exists. So it has to have begin having its own life, so to speak, because it's right in the middle of the architecture, engineering, and other disciplines, and it's getting so big that it has to be somehow start its own journey.
Another one here.
Hi, Milos. Did you say that there is no professional identity, that you must create the identity? Do you think that you incorporated the structural analysis and coding and a lot of things in your work? And do you think that architects must know everything, or the work must be collaborative? And how do you think you must to teach for graduating students? You must to teach this kind of things, or no? What do you think?
Yeah, it's a very complex question, and I think that the architecture suffers because it's trying to encompass too much, and it needs some kind of separation. How that will happen, I don't have an exact idea, but that's why this is happening. That's why we all create our own identities. That's why I am an architect, and some urban planner is an architect, and we are all architects, but we actually are more different between each other than between me and some other profession. I'm much more similar to the programmer or the structural engineer. So that's a big question, how to create the curriculum. And if it's I guess the idea is to learn everything, just a little bit, but not for a long time. Not for a long time. Basically to inform people until the second or maybe third years of studies, and then to make them choose the direction they want to go, because the directions are so big that they need some kind of separation. The architect, the term architect is just too big now. It's extremely big.
Other questions? Yes.
Thanks, Milos. That was fantastic. Just to take the conversation in a similar direction, some firms who are sort of working in those interstitial spaces, who already have maybe a higher ratio of programmers to architects, would still acknowledge that there's a certain dogmatism around programming and there's a certain sort of creative thinking around architecture. I mean, would you acknowledge that you still are an architect and a programmer in one person, and you're maybe bringing some of those that creative thinking and problem framing from architecture into your programming?
There are certainly certain advantageous things that I have, because I can understand architects and I can understand engineers when they can't understand each other, and when I stand in between, it helps me. But I am very far away from classical architects. So the architect in me is just a part of me that helps me do my work. It's not necessary. I have to admit, I don't think it's necessary, but it's really helpful in a way. So I would never get rid of it. It does help a lot, and that's why when you do things like this, you have to have a very, very broad knowledge. I usually say in my videos that you can't get rid of the architect in you, you can't get rid of the engineer or the programmer. You really have to know very well all those fields so you can do something like this. I also had to learn a lot about static analysis. Otherwise, I couldn't program the details.
More questions? We still have some time? Yes, over there.
Hello. It was very nice, your presentation, and I also liked very much that you did your plugins for download. Yeah, people can download it for free.
Yes.
It's very nice for you to do this. Yes. And have you heard about the microbit?
No.
It's a program it's a computer from BBC, the broadcast company. That just last Tuesday, she just showed it's a small computer that has compass, accelerometer, processor, LED display. And the question is because they say they're going to give it for 1 million children from 11 years old in UK, of course. It's a British program. So maybe that's one step to see since the beginning, if we have a new generation of kids that from 11 years old can start coding program. When they go to architecture school, they're going to have their head like this size and very open to program and be architect in the more traditional way, maybe.
Yes, probably that will happen. But it's always connected. Then this will go much higher, you know. Then this will go into neural networks, artificial intelligence, genetic algorithms, so there will always be a separation. It's just everything goes together. But that's a natural way. Of course, everybody will learn how to program. I mean, you have many applications nowadays for kids to do that. And when it comes to that, it's really not a question anymore. It shouldn't be discussed anymore. Everything is becoming software. 90% of the world will be software very soon. So the software has its own language that we have to speak.
Okay, I'm sorry if I will spoil a little bit the theme of the conversation. I was more interested in a particular aspect that you mentioned. You showed one of the projects where you had the whole components modeled in CATIA. This is a full parametric tool, yet you still had to program in order to find out where they were located. It's hard for my mind to understand why something which is so highly parametrical should be able to provide you this information. Why would you need a programming layer on top of it? Or was it because it was first developed by someone else in CATIA, you just got the product, didn't have everything else you needed, or knowledge.
I just showed that project as an example of bad organization and why you need to organize it better and have the programmer from the beginning. What they did was that all this 3D geometry, it was done in Rhino and whatnot, and then all those surfaces were given to a company that divided that surfaces and made those models in CATIA, those complex elements. But once they made them, they, for some reason, put them all in 2D on a coordinate beginning. And when they delivered them back, it comes to this organization, when they delivered them back, the people were not sure if they fit anywhere in 3D. So if I was there or anywhere else were there from the beginning, this would never happen. You would have this automation and the building of elements already automated in 3D. But because of this separation of work, and because of this neglect of what can be automated, this is what happens. And then this is why I had to make an incredibly complex algorithm, probably the most complex that I have yet created, to do something that shouldn't have been done in the first place. Yeah, you're right.
Yeah, okay, agree. Thank you for the clarification. Interesting problem.
There's one in the back also later on.
Really like the presentation. You show, it's just a detail, but you show the nightmare with the PDF when you get into the constructor for the brackets. And I experienced the same thing in practice also. You want to do something parametric and you want to keep the model as the information, and at the end you have to translate different representation for different labor. And what do you think we should do to change that? Is it possible to change that? Is it a matter of regulation, or is it just old practices? Can we use AI? I don't know. That is really the pain point, I think.
It's not a matter of regulation. It's just a matter of bad practices and people being comfortable and don't want to change things. Especially if you go to big companies and you tell them, okay, can you now change everything? And they don't want to do it. And that it makes you angry. And then you think, okay, I'm going to make my own company with my own machines and I'll be more effective than you. But I don't have millions of dollars for the machines, so I have to still put up with it.
Thank you, Milos, for your presentation. Mark Barry wrote in his book, Scripting Cultures, that many of us are copying and reusing code. What do you think about the share the code?
The sharing of the code?
Sharing, yes.
Yes, of course, that's the future. That's why I'm doing these free plugins. I'm not sharing the code because it's very complex, but the open source coding should definitely be the future. And I always admire people that are pioneers like that, pioneers in that field, like Linux and other open source software. So I'm all for it. That's my attitude, basically. It's not such an easy thing. That's the problem. Every programmer knows how complex their code is and that they cannot read it after 2 months if they forget about it. But it has to have a very, very good organization, and that's why it goes very slowly, and a very small number of people usually participate in these open source programs. But you just have to work on it to make it more understandable and better, and many people are doing that.
Hi, Milos. First of all, I like your idea that the computation is kind of creating a new map for the design profession. So right now, some of the cases we have a very defined profession of consultancy or automation for construction and design. But there are still, I think, many places that are not well defined. And at the same time, AI has a big change from the AI that you're talking about is considered, like, for some authors like Jason Brown, like a different AI that from the 60s and 70s. This is like a scruffy AI that deals with inductive frame and a strategy framework, so you can deal with problems that you don't need to describe that much, so the AI can find some solution. But the things that you also talk that in your practice you work in a very specific way, that you have some well-defined design or surface, and then it's kind of your task is well defined, and you try to optimize it. But you also talked about the early stages of designs in which you could also think about automation. And I would like you to, talk about your thoughts about how far can automation deal with problems that are not so well defined, and sometimes you need to explore more than optimize. So what do you think are what's the future for that automation in early stages of design?
Well, that was the point I'm trying to make, as I said, my work starts when the design phase stops. I rarely had to deal with the design phase because it's very complicated, and the tools we have are not up to the task, definitely not. The Grasshopper and stuff like that, it's very interesting for experimenting, but the practice says that after 2 months of experimenting, people usually just give up because the limitations are too big and do something by hand. Not always, but in many cases. And that's why I recognize that we are still far away from actually using automation in this design phase, and I concentrated on this one. But this idea that I have about the artificial intelligence software, the weak artificial intelligence software, is basically designed with that intention, to enter the design phase. And that's the way to do it, with the feedback between the computer, between the human and the machine, in which you would start the design very simply, give 3 points for a bridge, and then the computer would design something stupid. And then you would say, this doesn't work. I will draw you a line, keep the bridge on this line. And then the computer would give feedback with some structure. Then you say, no, I want this surface here, incorporate that into design. And in this feedback, where you always correct the machine, but the machine is able to do millions of calculations that you can't do and give you the best solution for your criteria. In this feedback loop, that's how you can do the automation in the design phase.
Yeah, perhaps. Okay, last question. Can you wait for the microphone, please?
Sorry.
Yeah.
Well, just on that, why haven't you pushed it in these directions?
Why haven't I tried that before?
Yeah,
Yes, I will tell you one word, and with that I will conclude my lecture. Time.